Okay, thanks to everybody. Today we'll start a new chapter on transformation, especially a very important transformation in the application of engineering, Laplace transformation. You must know about the scientist Laplace. Today we'll try to understand the what is Laplace transformation and what is its application in engineering. And so today we'll discuss about an introduction to Laplace transform and its application in engineering. First of all, we will discuss what is Laplace transformation and a historical background on Laplace transformation. Actually, you must know about this scientist, whose name Pierre Laplace. According to his name, this transformation name, he was also known as Franz Newton, a very famous scientist and mathematician. So he's the founder. Pierre Laplace is the founder of Laplace transformation. First of all, he developed mathematics in astronomy, physics, and statistics as a scientist and began to work in calculus, which led to the Laplace transformation. When he went to work with calculus after Newton, he got many problems and faced many problems. So he invented a new concept, Laplace transformation, and using this transformation, actually, he solved many well-known problems in the history of mathematics. So focused later on celestial mechanics on the first scientist to suggest the existence of black holes, a famous scientist actually. Now, history of transformation. There are different types of transformation. So I am discussing a history about this. Euler began looking at integrals as solution to the differential equation in the mid 1700s. So you must know Euler, a great mathematician. So first of all, in mid 1700s AD, he was looking at integrals to solve differential equations and using this transformation. So Lagrange took this a step further while working on probability density function and looked at the forms of following equation. You must know about the Lagrange. He was also a famous mathematician, and he worked on probability, and he also worked with this transformation. Finally, in 1785, Laplace began using a transformation to solve the differential equation of finite differences, which eventually lead to the current transformation. Actually, to solve a differential equation, he used this method. That means Laplace 1785 founded a nice transformation to solve differential equation. So actually, what is the definition of Laplace transformation and why we use this transformation? So first of all, the concept of Laplace transformation plays a vital role in wide fields of science and technology, such as electric and communication engineering. You're the students of what CCE, computer and communication engineering, look like this. So electric and communication engineering is very important for you, and quantum physics, solution of partial differential differential operations, etc. And this actually this Laplace transformation will be a solid foundation in the fundamentals of and is gain understanding of some of the very important and basic application of this transformation, including Laplace transformation. So transformation in mathematics deals with the conversion of one function to another function that may not be in the same domain. So Laplace transform is a powerful transformation tool which literally transforms the originally differential equation into an elementary algebraic expression. This later can then simplify be transformed once again into the solution of the original problem. That means actually we need to apply this Laplace transformation to solve differential equations. And this transform is named after the mathematician and renowned astronomers Pierre Simon Laplace, who lived in France, and he also known as Franz Newton. Remember it. So very famous mathematician, and he is the founder of this method, Laplace transformation. So actually, what is Laplace definition of transformation? Actually, we have to work on function. Remember it. We have to remember work with a function. Suppose that f is a real complex valued function of the variable t, and time you must t can be taken as a time also, and t is a parameter. So and t is the positive one, positive parameter. So f is a real complex valued function of the variable t, and s is a real or complex parameter, and s will be the real or complex anyone, but f will be the real or complex valued function, and s will be the parameter. Then we can define Laplace transformation of f as this, like this: f of s equals to Laplace transformation of f of t. This read as Laplace transformation of f of t, and this equals to can be written as 0 to infinity an improper integral e to the power minus st f of t dt. And here remember it, t is the variable and s is the parameter. S may be real or complex. So this is the actually mathematical notation for Laplace transformation. And graphically we can plot like this: Laplace transformation of f of t equal to f of s can be written as like this. This is the domain t and this is the domain s. So because this is two domain, because there are two functions, one is f of t and another is f of s. This is the function of parameter s, and this is the function of variable t. Remember it. So this f of s equals to 0 to infinity minus e to the power minus st f of t dt is the definition of Laplace transformation. Now, existence of Laplace transformation. So there is a limitation for Laplace transformation. Suppose f of t must be a piecewise continuous function, which means that it must be single valued but can have a finite number of finite isolated discontinuities for t greater than 0. That means you must know continuous function, and in limit continuity you must know about this, but it is another part piecewise continuous function. That means where the whole function can be divided into some small pieces, and every pieces will be continuous at that defined interval. So it must be a single valued but can have a finite number of finite isolated discontinuities for t greater than 0. Not all will be continuous. So this is the and another one, f of t must have exponential order, which means that f of t must be remain less than m into e to the power minus at, that as approaches to t tends to infinity, where m is a positive constant and a is a real positive number. That means f of t must be less than this, and this is another f of t is the function of t domain, so this must be less than. So these two conditions must exist to for the existence of Laplace transformation. Now, elementary properties of Laplace transformation we'll discuss later. Linearity property, first translation or shifting property, second translation or shifting property, like this, and Laplace transformation for derivatives, Laplace transformation of integral, multiplication of by t to the power and division by t. So we'll discuss in later. Okay, and this is the main properties of Laplace transformation. And the Laplace transform basic function, this we'll discuss about this now. So Laplace transformation, from the definition we found that actually f of t be any given function on interval t then its Laplace transform is defined as like this, where this is the transform and given function f of t. Remember it. F of t will be must be given function, and Laplace transform function will be f of s. And s is the parameter, t is the variable, and s is the parameter which will be real or complex, and f of s also real or complex. So Laplace transform is an improper integral. Remember it. Laplace transform is an improper integral. Similarly, we can write inverse Laplace transformation like this. If f of s equals to Laplace transformation of f of t, then inverse Laplace transformation can be written as like this. Inverse Laplace transformation of f of s equal to f of t, just opposite. So this is the given function for inverse Laplace transform, and this will be the inverse transform. That means opposite of Laplace transform. So inverse Laplace transform is a complex integral, not improper integral. Remember it. Complex integral. So some basics we can find some basics. So basic example. Suppose Laplace transformation of 1, what will be? Okay. Laplace transformation of 1, how we can get? Actually, from the definition, Laplace transformation of f of t equals to f of s, this. Okay. From the definition, we get 0 to infinity f of t e to the power minus st dt. If f of t equals to 1, then we can Laplace transformation of 1 will be 0 to infinity f of t equals to what? 1 e to the power minus st dt. Just integrating this improper integral will give the result of Laplace transformation of 1. So this equals to minus 1 by s e to the power minus st, and upper limit will be infinity and lower limit 0. You must know e to the power minus e to the power x formula what? E to the power x. Just dividing with the coefficient of t, because with respect to t we are integrating with respect to t. So e to the power minus st, e to the power minus st, integration what? E to the power minus st, but dividing with the coefficient of what? T. Coefficient of t what? Minus s. This is why dividing with the minus s we get this one. So putting upper limit in replace of t, e to the power minus infinity. E to the power minus infinity what? 1 by e to the power infinity. 1 by e to the power infinity what? 1 by infinity. So 1 by infinity means 0. So after putting infinity in replace of t in the function e to the power minus st, we get 0. So if then minus and putting lower limit in replace of t. So if t equals to 0, then this value what? E to the power 0. E to the power 0 means what? 1. So minus 1 we get. So minus 1 into 1 minus 1 by s, the result will be what? 1 by s. Similarly, we can find out Laplace transformation of e to the power at t. E to the power at t, Laplace transform what will be? By the definition of Laplace transform, definition of this, remember it, we are using just in replace of s, we are putting the function, given function. So Laplace transformation of e to the power at t will be Laplace transformation of e to the power at t equals to 0 to infinity e to the power at t into e to the power minus st dt. Just in replace of f of t, we are putting this e to the power at t. Okay. In replace of f of t, we are putting this. Now, e to the power t into e to the power minus st can be written as e to the power s minus s minus a into t. Okay. So base same and power will be added. So e to the power minus s minus a into t. Now integrating e to the power e to the power e to the power x e to the power x formula what? E to the power x, but we have to divide with the coefficient of t. Coefficient of t what? Minus s minus a. So dividing with minus s minus a, we get the this line. Now putting upper limit in replace of t, we will get 0. E to the power minus infinity what will be? 0. And putting lower limit e to the power 0. So 1. Similarly, like this, we get 1 minus 1 divided by s minus a, where s greater than a. Remember it. But here s greater than 0. S is the parameter. And this parameter will be greater than what? A. So we use Laplace transformation. This Laplace transformation help in solving the differential equations with boundary values without finding the general solution and the values of the arbitrary constant. The main aims to use this transformation in engineering is this. So we must know about the definition. So Laplace transformation of f of t can be written as f of s equals to 0 to infinity to the power minus st f of t dt. Okay, and the provided integral exists. This in improper integral must exist is called Laplace transformation of f of t, and it is denoted by like this: Laplace transformation of t equals to f of s 0 to infinity e to the power minus st f of t dt. So some formula we can use. Actually, Laplace transformation of 1 by s, we have proved this. Okay, and Laplace transformation e to the power at what was 1 by s minus a. And Laplace transformation of sun hyperbolic, Laplace transformation of t to the power n, what will be n factorial divided by s to the power n plus 1, where n equals to 0, 1, 2, 3, dot, dot. And number 4, basic Laplace transform. Laplace transformation of cos hyperbolic at what will be s divided by s square minus s square, where s square is greater than s square. Similarly, number 5, Laplace transformation of sin hyperbolic at equals to what will be a divided by s square plus s square, s divided by s square minus s square, but here s square minus sin hyperbolic t and cos hyperbolic t, this a divided by, remember it, but here s divided by. So there is a similar formula of Laplace transform, but here in numerator s for cos hyperbolic t, and in numerator a for sin hyperbolic t. So Laplace transformation of sin a t, what will be a divided by s square plus s square. For sine we have to use a, and for cos we have to use s. Remember it. For cos we have to use s, a parameter in numerator, and here also in numerator we have to use s parameter. So we have proved this Laplace transformation of 1 by s. We have proved this. So according to the definition, Laplace transformation of 1 equals to what will be 0 to infinity 1 into e to the power minus st dt, and this equals to what? Integration of this e to the power minus st formula, what will be e to the power minus st, dividing with the coefficient of t. Coefficient of t what? Minus s. So and upper limit will be infinity and lower limit 0. So this equals to minus 1 by s and 1 by e to the power st. That means putting upper limit, we get 1 by e to the power infinity. 1 by e to the power infinity means what? 1 by infinity. Remember it. 1 by infinity means 0. And putting lower limit minus, putting lower limit e to the power 0 what? 1. This is why only 1 by s we get. Minus minus plus. So this is the first proof of first formula. Similarly, second one, Laplace transformation of t to the power n equals to n factorial divided by s to the power n plus 1, where n and s are positive, must be positive. Now we'll try to prove this basic formula of Laplace transformation. So Laplace transformation of t to the power n will be 0 to infinity e to the power minus st. In replace of f of t, we are putting what? T to the power n. Okay, because f of t equals to what? T to the power n. Now substituting st equal to x equals to what will be? X by s from this. Now dt what will be? Dt what will be? Dx by s. So substituting these values we get what? Laplace transformation t to the power n will become 0 to infinity e to the power minus x, because st equal to what? X. This is why it becomes minus x, and t equals to what? X by s. So t equal to x by s to the power n, and dt what will be? Dx by s. So dt, in replace of dt we are putting dx by s. So this imply Laplace transformation of t to the power n equals to 0 to infinity, and s how many here? S to the power n, and here another s. So s to the power n plus 1 will be in denominator. Okay, how many s? S to the power n here and another s here. So s to the power n plus 1 in denominator. So 0 to infinity and e to the power minus x, e to the power minus x, x to the power n dx. You must know about this formula. This is the gamma function. Okay, we can use gamma function here from the properties of definite integral. Gamma beta function, you must know about this in the definite integrals. So Laplace transformation t to the power n can be written as 1 by s to the power n plus 1. This equals to what? Gamma n plus 1, because gamma n plus 1 equals to what? 0 to infinity e to the power minus x to the power n dx. Remember it. But gamma n equals to what? N minus 1. They are n minus 1. If we replace n equal to n minus 1 here, then we can get the original gamma function, gamma n. Okay. So this is the formula of what? Gamma n plus 1. So Laplace transformation of t to the power n can be written as gamma n plus 1 means what? N factorial. You must know about this relationship. So n factorial divided by s to the power n plus 1 is the Laplace transformation of t to the power n. This is the second formula. Similarly, third formula, we have proved this Laplace transformation of e to the power at 1 by s minus a, where s greater than a. So this is Laplace transformation e to the power at will be, in the place of f of t, we are putting e to the power at. So it can be written as e to the power minus st plus at dt. Now we can arrange this 0 to infinity e to the power minus s plus at. That means minus s minus a into t. Now e to the power minus e to the power mx formula. So e to the power mx dividing with the coefficient of m. M means what? Minus a bracket s minus a. So similar formula using. So we get 1 by minus 1 by s minus a, and putting upper limit in the place of t, because we are integrating with respect to t. This is why this is the t values. Upper limit and lower limit will be t values. So putting upper limit in the place of t here, we get 1 by e to the power infinity. So 1 by e to the power infinity. Understand? E to the power minus s minus I t can be written as 1 by e to the power s minus I into t. Negative sign will be cancelled because of inverse. So putting upper limit, we get 0, and putting lower limit, e to the power 0 means 1. So we get easily 1 by s minus a. Now another one, Laplace transformation of cos hyperbolic at can be written as Laplace transformation of cos hyperbolic at. You must know this. This is the relation between, in complex number, you must know cos hyperbolic at equals to what? E to the power at plus e to the power minus at divided by 2. This is the relationship between hyperbolic function and exponential function. From complex number, you must know about this. So Laplace transformation of these two, this whole function, cos hyperbolic at equals to this one. Now this can be written as half Laplace transformation of at plus half Laplace transformation of e to the power minus at. So Laplace transformation of at, we found this 1 by s minus a. Okay, 1 by s minus a. Similarly, Laplace transformation of e to the power minus at, what will be? 1 by s plus a. Just putting a equals to minus a in this formula, we get 1 by s plus a. So Laplace transformation of cos hyperbolic at equals to taking LCM s minus and s plus a, we get s divided by s square minus s square. Okay. Similarly, sun hyperbolic at can be found. Laplace transformation of sun hyperbolic at equals to Laplace transformation of this. This comes from where? Look like this formula, cos hyperbolic at equals to this. So sun hyperbolic at equals to what will be? What will be? It just minus like here. Okay. Now same formula, just negative sign. So half into Laplace transformation e to the power at minus Laplace transformation of e to the power minus at. So we get Laplace transformation of this 1 by s minus a from here. Okay, and e to the power minus at, similar formula, s plus a. So after taking LCM, we get a divided by s square minus s square. Very easy formula for it. Similarly, Laplace transformation of sin at, what will be? Now sin at equals to, can be written as what? Sin at equals to what? E to the power at minus e to the power minus at divided by 2 y. This is the formula of what? Sin at. Relation between trigonometric function and exponential function. From complex numbers part, we studied this. So sin at equals to Laplace transformation of e to the power e to the power iat minus e to the power minus iat divided by 2 I. So we can divide it into two parts, Laplace transformation of this minus Laplace transformation of this. So e to the power iat can be written as 1 by s minus a using same formula. In the place of a, we are putting ai in the formula. One Laplace transform minus ait will be 1 by s plus ia. So taking LCM, we get this. So ii will be cancelled and I divided by s square plus s square. Similarly, Laplace transformation of cos at equal to s divided by s square plus s square also found using this relation. Cos at equals to what was? e to the power iat plus e to the power minus iat divided by 2. So, but in sine, we have to use negative sign. Similar formula, but for sine, we are using minus sign, and for cos, we are using plus sign. Same formula. So, same method, Laplace transformation e to the power iat will be 1 by s minus ia, just using plus sign. Same procedure, s divided by s square plus s square. Now, find another one example. Find the Laplace transform of f of t defined as f of t equals to t divided by k when 0 less than t less than k, and f of t equals to 1 when t greater than k. That means this is the piecewise function. So f of t has different value for depending on t. Now the Laplace transformation of f of t can be written as this whole integral, improper integral, will be divided into two parts. One will be 0 to k f of t e to the power minus st dt plus k to infinity 1 into e to the power minus st dt. That means by the definition, we can write using the properties of definite integral, 0 to infinity can be divided into two parts, 0 to k f of t e to the power minus st dt plus k to infinity f of t e to the power minus st dt. But here f of t value what? Between 0 and k, f of t value what? T by q. And when t greater than 0 k, that means t up to infinity k, so then f of t what will be 1. So we can divide it into two parts. By the definition, we can write this. Now this equals to 1 by k will be common for the first one, t into e to the power minus st dt. So it t into e to the power minus st dt. This is the UV formula. Okay, t into e to the power minus st, the integration of e to the power minus st, integration of e to the power minus st, what will be e to the power minus st?
Sir, first line কিভাবে করছেন স্যার বুঝি নাই স্যার এটা। জি স্যার।
From Fourier series, from Fourier integral, we must use this concept because this t divided into two parts. One is 0 to k, 0 to k. T lies between 0 to k. So taking integration between this. Then another one, what? T greater than k. That means k to infinity. Okay, greater than means what? Up to infinity. This is why this total interval 0 to infinity divided into two parts. One is lies between 0 and k, and another one k into infinity. Okay.
Yes, sir.
0 to infinity divided into two parts. And for the first part, f of t value what? T by k. And for the second value, second part, f of t value what?
1, sir.
1. So here k is the constant because with respect to t, integration is with respect to t, so k is the constant 1 by k. So t into e to the power minus st dt will be integrated. So UB formula you have to use. So u into t into integration of e to the power minus st, what will be e to the power minus st dividing with the coefficient of t. Then limit will be 0 to k minus differentiation of t. Differentiation of t what? 1. Integration of this. Integration of e to the power minus st, and this minus s exists, and dt. Now second part, e to the power minus st formula what? E to the power minus st for integration will be e to the power minus st divided by minus s, dividing with the coefficient of t, and limit will be k to infinity. Okay, for the second integration. Now from this one, we are getting 1 by k and putting upper limit here, k into e to the power minus k s divided by minus s. In replace of t, we are putting k here. Then my putting 0, we get 0. Okay, so 0 not affected here. Minus this
Sir,
integration can be written as e to the power minus st. What?
Sir, আমরা কি স্যার কে টি এর ভিতরে স্যার কে এর ভ্যালু আপার লিমিট লোয়ার লিমিট গুলো বসাবো স্যার?
In replace of k, upper limit. In replace of we have to put t equals to k. T equals to k here. Because these are t values. Yes, you are right. Putting t equals to k here, we get this. Okay, but putting t equals to 0 here, we get 0. So for lower limit, we get 0 values. 0 into something means what? 0. So for the second part, we are getting e to the power minus st integration. What will be e to the power minus st integration? What will be e to the power minus st dividing with the coefficient of t. Coefficient of t what? Minus s. So minus s what will be? S square. And taking limit within bracket, upper limit k and lower limit 0. And this values what will be? E to the power minus putting t equals to infinity, we get e to the power infinity what? Minus infinity what? 0. Okay, e to the power minus infinity what? 0. And putting k lower limit, e to the power minus kt, e to the power minus ks. Okay, minus ks divided by minus s. And minus another minus from where? Because we have put actually lower limit, and before lower limit we have to use minus. So minus minus what will be? Plus. Okay, now putting upper limit in the place of t, e to the power minus sk. Okay, then putting 0, we get what? E to the power minus 0 what? 1. So 1 by s square, 1 by s square. And this is the last part. So from this whole part, we can write e to the power minus sk divided by s, take 1 by k multiplying. Okay, 1 by k means what? Cancelled. So first part, and this is the 1 by k into second part, 1 by k into third part, and this is the last one. So taking LCM, ks square, we get this only, because e to the power k minus ks divided by s, and this will be cancelled. Okay, and this first part and last part will be what? Cancelled. Minus and plus, this is why. So 1 by ks square common, then we get right this. Very interesting example. First example. Okay, now another example. To find the Laplace transform of the function f of t minus 1 when t lies between 1 and 2, and f of t equals to 3 minus t when t lies between 2, 3. The given function is a periodic function with period actually what? 3. 1, 2, 3. Okay, so Laplace transformation of f of t can be written as what will be? Integration what will be? Integration limit 1 to 3 f of t e to the power minus st dt. Now between these two limits 1 to 3 divided into two parts, 1 to 2 f of t e to the power minus st dt, plus another one 2 to 3 f of t e to the power minus st dt. Similarly, putting the functional value f of t equals to what? T minus 1, and f of t equals to second value what? 3 minus t. Now just using integration, definite integrals, and UB process, we can write u into e to the power minus st integration will be this minus t minus 1 differentiation what? With respect to t 1, and again integration of this what will be e to the power minus st and minus s whole square, because again dividing with the coefficient of t. So and within bracket we are putting upper limit 2 and lower limit 1 of this integration. Now similarly, UB process, we get this integration u into integration of e to the power minus st into the integration e to the power minus st, what will be? E to the power minus st dividing with the coefficient of t, plus 3 minus t differentiation what? Minus 1. So minus minus plus here, and integration of e to the power minus st, e to the power minus st, and dividing with the another coefficient of t minus s. So minus s minus s minus s whole square, and putting the limit upper limit 3 and lower limit 2 for this integration. Now just putting t equals to 2 here, and t equals to 1. T equals to 1 will be, it will be 0. 1 minus 1 what will be? 0. So we get only this one. Now if t equals to 3, this will be 0. Okay, and t equals to 3, then we get this line, and if t equals to 2, then we get 2 minus 1, 3 minus 2 means this only. This very easy, just adding and subtracting, we get this line. This is the result. Similarly, we can solve the Laplace transform of these types of function. Okay, there are three parts of this function f of t. F of t equals to 1 when t lies between 0 less than less equal to t less than 1, and f of t equals to t when 1 less equal to t less than 2, and f of t equal to t square when 2 less equal to t 10 less than infinity. That means this function, there are three parts. So Laplace transformation f of t equals to 0 to infinity e to the power minus st f of t dt. According to the definition of Laplace transformation, we can write down this. Now, f of t values we are putting for different values of function. So 0 to 1 will be f of t equals to what? 1. And 1 to 2 integration f of t equals to what? Only t. And 2 to infinity, what will be? T square. F of t equals to t square. Just three parts using the given function. Now, taking integration, this integration very simple. Laplace transformation of 1. Okay. So, and this is Laplace transformation of t into e to the power minus st, this UV process. T into e to the integration of e to the power minus st and minus differentiation of t what? 1 with respect to t. So again integration of this e to the power minus st divided by s square, putting the limits. Similarly, again UV process, t square e to the power minus st integration what will be? T square into e to the power minus st integration minus to t square differentiation what? Twice t. And again integration of this e to the power minus st will be e to the power minus st dividing with the coefficient of t minus s minus s. Okay. Again the integration of this UV process. So we get this as a whole. Okay. So this integration UV process, we get this one. U into integration of b minus differentiation of u and integration of b. So very easy for you. And this 4 example 4 will be homework for you. Okay. And t lies between 0 and 2, t square f of t equals to t minus 1 when t lies between 2 and 3, and f of t equal to 7 when t greater than 3. Similarly, using the definition of Laplace transformation, and this total functional value 0 to infinity can be divided into three parts. One is 0 to 2, and f of t equal to what? T square. Another one t 2 to 3, integral limit what? 2 to 3, and f of t value what? T minus 1. So, and t to infinity, 3 to infinity, t values, and f of t equals to what? 7 only. So, integrating this one, you must know this process of chain of integration of chain in our previous lecture. We use this in Fourier series and Fourier transform also. So, UV process, just UV process, t square into e to the power minus st integration. E to the power minus st integration what will be? E to the power minus st dividing with the coefficient of s, and differentiation of t square what will be? Twice t. Okay. Again integration of this e to the power minus st, this whole integration what will be? E to the power minus st and minus s whole square. So again differentiation of twice t. Differentiation of twice t what? Only 2. So again difference integration of this what will be? E to the power minus st and dividing with the coefficient of t, that means minus s. So how many minuses here? 3. So minus s whole cube, and limit will be what? 0 to 2. Similarly, integrating by parts like this, t minus 1 u into integration of e to the power minus st will be this minus t minus 1 differentiation what? 1. So again integration of this will be e to the power minus st minus s whole square. Okay. Now 7 into this will be, this integration will be only 1 by s. So after putting limit, we get this line. Very easy for you. I hope if you do practice at home, you can do. Now adding and subtracting all these values, we get this result, required result. Now similarly, how to find the Laplace transform of 1 plus sine twice t. Okay. Now Laplace transform of 1 plus sine twice t. This is the f of t. Remember it. According to the definition of Laplace transformation, 0 to infinity to the power minus st f of t dt. Okay. F of t equals to what? Given function. So sine twice t means you must know by using the relation between t unit t function and exponential function. From complex number, you must know about this formula. E to the power twice it minus e to the power minus twice it divided by twice I. So sine twice t equals to this formula. Now multiplying this, we get three parts here. Okay. E to the power minus st1 first part, e to the power minus st into e to the power twice it second part, e to the power minus st, and third one third term. Now just integrating with respect to t, we get this one. And putting upper limit infinity and 0 to e to the power minus st, integration what will be? E to the power minus st dividing with the coefficient of t. Coefficient of t what? Minus s, dividing with the coefficient of t minus s. So another one similar, e to the power minus x formula, e to the power minus x dividing with the coefficient of t. Coefficient of t what? Minus s plus twice i. Okay. Similarly from the third one, e to the power minus minus s minus 2i t, integration what will be? E to the power mx e to the power mx dividing with the coefficient of t minus s minus twice a. So putting upper limit and lower limit, we get this one. Putting upper limit infinity, you must know this becomes 0, this becomes 0, this becomes 0 also. Okay. So only after putting lower limit, we get twice I by s. E to the power minus 0 means what? 1. So 1 by this, 1 by this. Very easy example for you. Table. Laplace transform, the elementary Laplace transforms, f of t equals to inverse Laplace transform f of s, and this is the Laplace transformation of f of t. So if f of t equals to 1, then Laplace transformation of what will be? 1 by s. We have proved this. And Laplace transformation of e to the power at will be 1 by s minus a. And e to the power n, we have proved this result. T to the power p also like this. And similarly, sine at this, and cos at this one, sine hyperbolic at this one, cos hyperbolic at is divided by s square minus s square, where s greater than absolute value of a. Remember it. And a must be positive. E to the power at sine bt will be like this, and e to the power at cos bt will be this one. So t to the power n, e to the power m, where n is a positive number, Laplace transformation will be like this. So we have to remember this table. And there are actually 19 Laplace Fourier Laplace transform formula, and you have to remember this, and we have to try to prove this. About 8, up to 8 we have proved result. Okay. So remember about this table, Laplace transform. এক minute, wait a minute please. The definition transform, what is actually transform? By the definition, transform a mathematical conversion from one way of thinking to another, make a problem easier to solve. Problem of original way of thinking, then you can transform it to solution in transform way of thinking, then inverse transform, and this inverse transform will give the solution in original way of thinking. So the problem in time domain, Laplace transform will give solution in as domain, and inverse Laplace transform will give the solution in time domain. Remember it. So we have studied about the another. There are any other transforms. Suppose Fourier transform, Z transform. We have studied about this in previous lecture. So it has a first property about this. So Laplace transformation uh, can be seen like this. Time domain linear differential equation transform to time domain solution. And by using Laplace transform, a Laplace transformed equation, then using algebra, we get the Laplace solution. So Laplace domain or complex frequency domain is the actually uh, solution for the, will give the solution for the Laplace transformation. So we must have the idea about the complex plane, and in complex numbers we have studied about this. So you must know about this imaginary line, okay, and real axis. So it forms u equals to x plus iy. That means complex function, complex variable function. So in next we will study about this properties of Laplace transformation. So till then, this is the end of this introduction to Laplace transformation. So thanks to everybody. I hope everybody will practice it at home and follow this lecture. You must be able to solve any problem in Laplace transformation. Okay, thanks to everybody.
Thank you, sir.
Yes, sir.